We're going to look more closely now at the periodic trend, the atomic radius trend. Okay, and the first thing you want to do is write out the electron configurations for sodium, lithium, aluminum, and gallium, because we're going to use these for this video and possibly a couple others as well, but especially this video. Okay, so the first part we're going to look at now is the atomic radius trend for the periods. Okay, so if we look at the atomic radii, and we're going to look across the period and say what happens to the radius. We already did this in the last video. All right, we look at our little app here, and this is my atomic radius. We look across the period left to right, and we see that our radius decreases. So that one is easy. We're not going to use those lovely configurations yet, so it decreases. Okay, so we're going to look at the configurations for sodium and aluminum, which are the first two that we wrote out there, and I want to know, are all of the valence electrons in those elements in the same energy level? So I look at sodium and aluminum there. Okay, sodium has its last electron in a 3s, aluminum has its last electron in a 3p. So yes, they are both in the third level. One happens to be s, one happens to be p. But that doesn't really matter, because energy levels is talking about how far away or how big that particular shape is. Okay, so they're both the same size, they're just different shapes. So now we're going to kind of play with that and talk about exactly what causes the periodic trend that we see on the table. So it talks about opposites having to attract. So in the review video, it talked about positives and negatives. What's in your center? Well, positives are in my center, protons. Okay, and neutrons, but they're neutral. And then I have electrons on the outside. So what's going to attract? Well, my positive protons and my negative electrons. So that's the idea it's talking about. The center of the atom and the outside of the atom are what's going to actually want to attract. So if we look at sodium and aluminum, okay, all of the electrons are the same distance away. So sodium has 11 positives. It also has 11 negatives. Okay, but it has those 11 negatives in the kind of 1, 2, kind of third level. So if we talk about them kind of as like rungs on a ladder to make it easier, versus, I mean, they're actually shapes, 1s, 2s, 3s, okay? Whereas aluminum has 13 positives, and it still has those kind of 3 energy levels. So what's going to be just a stronger positive pull? 11 positives or 13 positives? Well, 13 is a larger number. So if I have 13 people pulling on something, that's a lot stronger than 11 people pulling on something. And think of it that way, because they both have electrons in the same distance away, that third level. So that's why aluminum is smaller in size. Okay, because if I look at my table, all right, and I compare sodium and aluminum, all right, you can't tell, but sodium is right there. Okay, we go across. Aluminum is right here. Aluminum has a size of 142. Sodium has a size of 179. So sodium is a little bit larger. Not by a lot, but it is a little larger. And it all has to do with that the electrons are in the same spot. Okay, third level. But aluminum has a stronger positive center to pull them in. There's a stronger magnet, so it pulls those electrons in tighter. Okay, so that's the harder of the two trends. We're talking about pulling and these electrons pulling. All right, now we're going to look at an atomic radius group trend, which is actually the easier one. Okay, we look in the groups, and we look down the group from top to bottom. It's a lot easier to see that the bottom ones are a lot larger than the top ones. So they should be increasing as you look down the periodic table. So then why does the group trend we see make sense? So I'm going to compare again and talk about two of them that are in the same group. So I'm going to say, okay, if I look up, we'll see, and I'll use a different color here, sodium and lithium are in the same group. Okay, lithium only has 3 electrons, so it ends in a 2s, but sodium has 11 electrons, and it ends in a 3s. So say, okay, they are a 2s versus a 3s. Well, if lithium has a 2s, or ends as its biggest one, sodium ends as a 3s as its biggest one, well, what's larger? The second energy level or the third energy level? The third energy level. So this one's a lot easier to talk about because you're dealing with a larger last energy level. So that would still hold true with the one below sodium. It would be in the fourth row, so it would be the fourth would be the biggest energy level. Now, nothing would be complete without an exception. All right, we're going to look at aluminum and gallium and see the radius for each one, and then what happens to it, and does it follow the right trend? Well, since it's an exception, we don't know that it doesn't, but okay. Aluminum here has a radius of 142.2, should be getting larger, but if I look at gallium right below it, it's 140. So not by much, but it isn't. Okay, aluminum is 142 picometers, gallium is 140. So it should be getting larger, but it actually gets smaller. So no, it does not follow the right trend. Gallium is actually smaller than aluminum. And we're going to talk about why. All right? So how are the periods that these two elements are in different from one another? So what precedes gallium that doesn't precede aluminum? So let's look here. All right, we're going to look at these last two things. All right, I have aluminum and gallium. Okay, aluminum's 1s2, 2s2, 2p6. Okay, gallium's a little bit longer. All right, and you see where gallium ends, and I'm actually missing one for gallium. Gallium should also have 4p1 there. Whoops. Okay, but anyway, if I look at those two there, okay, you see in front of gallium, it has all these 3Ds. And so when I see gallium, gallium has all those electrons there in the transition metal. So what happened with gallium is you stuck a bunch more electrons into the third energy level because it was 3. So you actually went down a level and stuck 10 more electrons a little closer to your nucleus. So that makes it actually be a little bit smaller because there's so much more in between there that those protons can pull on. So those D block electrons are what kind of throws this exception off, or causes this to be an exception. So again, gallium has the D block electrons. You're adding more electrons to the same level, the third level, and this outweighs adding one more in that fourth P. So even though it's a bigger level, you're adding so many more in between the third, it outweighs it. This is just one more way to view the atomic radius trend. Okay, notice how we have atomic number on the bottom, we have atomic radius on the top, going on the y-axis. So as we look across, if I go from lithium to neon, that's the second period. And what happens to our radius? It goes downward because you are increasing an atomic number, which means I'm going left, well for you, left to right across the table. Okay, and I'm decreasing. Well, you notice, again, period 3, left to right across the table, increasing atomic number, and you're decreasing. But if we look at lithium to sodium to potassium to rubidium to cesium, those are all on the same group. Okay, and what do we notice about those? Well, they increase. So just one more way to kind of graphically show the atomic radius trend with actual numbers versus the pictures.